Hi everyone, and welcome to Introduction to Attention. I'm Killian Menton, and this video is the third in our series where we'll be implementing AlphaFold from scratch. Attention is a relatively new concept. In 2017, Google released a paper on its transformer architecture for natural language processing, giving the paper the name "Attention is all you need," and so far it has lived up to its reputation. You'll have a hard time finding a modern breakthrough in machine learning that doesn't use attention as its core mechanism. And like most clever ideas in machine learning, its core idea is quite simple. Imagine trying to understand a complex sentence without knowing which words to focus on. This is where the game-changing concept of attention in machine learning comes in. The attention mechanism addresses the problem of handling sequential data, which is most existing data. Language is sequences of words, music is sequences of notes, and proteins are sequences of amino acids. The name attention comes from its idea to determine which tokens in the input are the most relevant for the task at hand, that is, which tokens the model should pay attention to, before basing its prediction on these attention weights. So far, we learned how to build machine learning models that solve vector-to-vector tasks. The network shown here is a visualization we've used in the last video to showcase a 2-layer feedforward neural network. It transforms a 784-element input vector, the image, to a 16-element intermediate, and finally to a 10-element output. We'll simplify our visualization a little to be able to visualize more complicated combinations of these operations. The colored squares denote vectors, and the nodes are operations or layers. This network uses a linear layer going from a dimension of 784 to 16, a ReLU layer, and another linear layer from 16 to 10 elements. Just remember that these nodes aren't magic, but concrete, simple operations. A linear layer means matrix multiplication, for example with a 16 by 784 matrix and sometimes with addition of a bias. And a ReLU layer sets all negative elements to 0. A network architecture like this, a stack of linear layers with nonlinearities in between, is called a feed-forward network. The question now is, how do we use these primitives to work on sequences? Say we've got a long sentence of n words, and each word is encoded as a 128-element vector. This is a typical starting point in text processing. Words, or parts of words, are replaced by integers using a so-called tokenizer, and then each integer is replaced with a learned feature vector. If we wanted to use this phrase as input to a feed-forward machine learning model, we'd basically have two options. Our first option is concatenation. We concat all the n words to an n times 128-element vector. This is called a fully connected architecture, and it captures the full information but has true drawbacks. First, the necessary weight matrix will get impossibly large for long sentences, and second, we don't have flexibility for input lengths, as the number of weights is directly proportional to the number of inputs. Our second option are recursive neural networks. We keep track of a hidden state ht that is iteratively updated by the words. We start with an initial state h0, for example h0 is equal to 0, and in each step we concat ht with the input xt and feed it into our neural net to compute ht plus 1. Note that we use the same model and the same weights for each time step t. After passing through all xt, the final output hn was influenced by all of the words and might be able to answer questions on them, like if the text was positive or negative, or if it contained the word dog. This has the advantage of having fixed number of parameters, independent of the input size, and that it can process arbitrarily long sequences. The major drawbacks are that hn has to summarize all the information of the whole sentence, which is a huge bottleneck, and that the encoding needs to be computed sequentially, because we need to know ht to compute ht plus 1. To the rescue comes the attention mechanism. It follows a simple idea. Every token in the input gives a quick summary on its content. The model creates a question and checks it against each of the summaries to get a score on how much it should contribute to the result. Then, each of the inputs is rated according to its attention score to compute the final result. Let's work through this step by step. The summaries are so-called key vectors. Each input vector x is mapped to a key vector by a linear layer. For the creation of the questions, or query vectors, we have several options. If we want to extract static information from the text, like the language it's written in, if it's positive or negative, or if it's truthful, we can simply use a static learned vector per query. These work just like the weight or bias parameters from the last chapter. We start with random vectors, calculate their gradients during training, and update them by gradient descent. To test how relevant the key is for the query, we compute the dot product of the two. We can do this efficiently using Torch.einsum as shown below. The dot product gives a score of how aligned the two vectors are. If they point in the same direction, the dot product is the product of their magnitude. If they are orthogonal, the dot product is 0, and if they point in opposite directions, the dot product is the negative product of their magnitudes. With the flexibility of learned parameters for the creation of the key and query vectors, we don't need a more complicated agreement metric. However, we usually use a scaled dot product, scaled by 1 over the square root of c, to make the computation more stable for different embedding sizes. So far, we got a matrix of raw attention scores of shape qk, where q is the number of query vectors and k is the number of key vectors, which is the number of inputs. We want the attention scores for a fixed query to be a distribution over the different inputs. For that, we need some kind of normalization. The typical normalization is the softmax function we've seen before. To generate the final outputs, we create a value vector for each input through a linear layer. Note that, just like for the key embeddings, we use the same linear layer for all keys and apply it to all the input vectors individually. These value vectors are scaled by the attention weights and summed up to create one output per query vector, as shown below. This is the full attention mechanism. We create key and value embeddings by applying linear layers to the inputs. For a set of query vectors, we compute the key query similarities as their scaled dot product. We normalize the attention scores with softmax. Then, we weigh the value vectors by the attention scores and add them up. In the end, we get one value per query. There are a bunch of small variations to this core mechanism, and we'll look at some of them next. Our first idea is to change up how we create the query vectors. For many tasks, the questions we want to ask are directly linked to the inputs, and static queries can't give this flexibility. Let's say, for example, we wanted to do translation from English to Spanish. To know which of the inputs is most relevant for the creation of the first output, we'd already need an understanding of the text. To get such an input-dependent query, we could pass the whole input sequence through a recursive neural net, like we've seen before, and use the final hidden state as our first query. With that query, we can calculate our first output using the attention mechanism. We can use the translated output to update the state in our RNN, use the next hidden state as the next query, and so on until we translate the whole sentence. Note that to realize this architecture, we'd also need special start and stop tokens to tell the RNN when the translation starts and to give it a way to mark that it wants to stop generating. One cool thing that we can do with attention is taking a look at the attention weights. Shown here is an example from a paper on machine translation using an architecture quite similar to the one we just looked at, but translating from English to French. In the picture, you can see which English words the network paid attention to generate each of the French outputs. What's really cool is that you can clearly see the network finding the correct words to attend to, even if they aren't the next one in the input. When translating the European Economic Area to La Zone Économique Européenne, the attention weights show the exact word in version order. Mechanisms like this, that we can use to actually interpret how a model made its decisions, are one of the key research areas of AI and AI safety. But while in this case explaining the attention weights worked pretty well, it often falls short for large models. That is because to be able to interpret why the model looked at specific neurons, we need to know what these neurons actually encode. And this often proves hard. Anthropic, the makers of the large language model Claude, stated like this. Unfortunately, the most natural computational unit of the neural network, the neuron itself, turns out not to be a natural unit for human understanding. This is because many neurons are polysemantic. They respond to mixtures of seemingly unrelated inputs. For this reason, interpretation of attention in large models often falls short of its expectation. The results of interpretation in the AlphaFold paper mostly state that in the early layers, attention focused on residues that are next to each other in the sequence, while in later layers, attention focused on residues that are next to each other in the protein. Basically, this just restates that the network indeed found out the correct structure of the protein, but tells us little on the question of how. But we aren't helpless. The explosion in large language models led to a huge increase in research on interpretability, driven by the big ethical questions that accompany their massive use. The paper from Anthropic we talked about earlier, for example, found a way to actually detangle that polysematicity and clearly label activation patterns. This process might be transferable to AlphaFold, possibly enabling us to tell in which stages AlphaFold starts coming up with hypotheses on commonly known structure motifs. This is one of the reasons why I think it's so important to not be too specific when learning AI. Many of the big breakthroughs came from taking a method that's commonly known in one area, like natural language processing, and taking it to a new problem, like protein folding. It's why we spent so much time talking about natural language processing in this chapter, and it's why I highly recommend you to also take a look at computer vision at one point or another, for example with the open material from Justin Johnson's course from the University of Michigan. Moving on with attention, we'll look at some variants to the general mechanism. The first is self-attention, and it is the form of attention that's used most. The only change is that the query vectors are generated from the inputs as well by linear layer. As a consequence, the number of outputs and inputs is identical. Often, the number of channels for the output is also chosen to be the same as for the input, so that the outputs and inputs have identical shape. To add some additional flexibility, AlphaFold often uses so-called gated self-attention with bias. The bias is an n by n tensor that's added to the dot product affinities before normalization. In AlphaFold, this is usually not learned bias but an n by n tensor that comes from a different computation in the model to allow for new channels of information. For example, in the Evo former, AlphaFold has a pair representation of shape nres-nres, where nres is the number of residues in the protein. The pair representation can build up information on the interaction between pairs of amino acids, and AlphaFold uses this tensor from the pair stack as a bias in a so-called MSA stack, where attention is performed on the amino acid sequence of shape nres-C. The gating part is simply another embedding of the inputs that's normalized by sigmoid layer to values between 0 and 1, and multiplied against the output from self-attention to limit how much information at this position should be passed on to the next layer. The last of these slight modifications to attention is multi-head-attention. Multi-head-attention means running multiple attention heads in parallel, concatenating the outputs, and running that through a linear layer to get it to a desired number of channels. However, we don't really need to use separate modules to construct this. It's in the nature of linear layer, that is, in the nature of matrix multiplication, that concatenating the output of two linear layers with the same inputs is identical to just using one linear layer and concatenating the weights vertically. In the same way, using two linear layers and adding up the results is equivalent to using one layer with the weights concatenated horizontally and concatenating the inputs. It's good to keep these equivalencies in mind as they are often used in machine learning without too much explanation. Knowing this, we can create the query, key, and value embeddings for the multiple attention heads jointly as a tensor of shape NHC. In our notation here, a linear layer going from Cin to HC means a linear layer going from Cin to H times C, followed by reshaping the output. Just like standard self-attention, multi-head-attention can also be combined with gating and with bias. The diagram shown here is the most general form of an attention module as we'll use it, and it's what we'll implement in the tutorial notebook for this video. At this point, we are finished with our gated multi-head-attention module, which is what's most important for actually implementing AlphaFold. What I want to do next is to take a look at some of the problems that emerge from the structure of attention and how we can solve them. The first in this list is the computational cost of attention. It's mainly driven by the dot product affinities and the attention weights, which have size n squared. For large sequence lengths, this has a huge memory footprint, one of the limiting resources in machine learning. In general, this is just something that we have to live with, and there are implementations of attention that can help mitigate this problem, like flash attention. If we have to work on really long sequences, however, classic attention is simply infeasible. In AlphaFold, this problem arises in the so-called extra MSA stack, where we do attention over a list of sequences in a genetic database that are somewhat similar to the target sequence. This can be up to 5,000 sequences and is more than what typical hardware can handle. To account for this, AlphaFold uses what they call global attention in the extra MSA stack. After computing the query vectors, they are averaged out, resulting in only one query. This translates to only one attention weight per key and one output. However, AlphaFold uses global attention together with the gating mechanism we've seen before. The calculated gate values have the same shape as the input, and so the number of outputs is restored by the broadcasted multiplication of the gates against the single attention output. Still, the single attention output is a big bottleneck, although necessary to handle the large count of sequences. The second problem of attention comes from the fact that each query can attend to each key. To see why this is a problem, let's take a look at the most prominent task for attention, next token prediction. The way that large language models work is by training them to predict the next words in the text sequence, one at a time. Translated into our attention module, it would look like this, where the outputs of the model should simply be the inputs but shifted down by one token. If we try to train this model, it would work really well. We can even make a good guess on how the attention scores would turn out. Like this, with most of the attention focused on the diagonal directly above the main diagonal. This is because, to predict the second word, it's really helpful to take a look at the one after the first. But if we try to do inference now, we run into a problem. Given the first token, the start token, the model will try really hard to get an attention update from the second token. Unfortunately, it can't do so, because the second token doesn't exist yet. It needs to be predicted from the model first. We trained the model to solve a task in a way that's simply not possible during inference. Luckily, there's an easy fix, and it's to use so-called causal attention masks. What that means is setting the affinities for all future keys to negative infinity during training. This translates to an attention score of 0 after softmax, and leads to a calculation of attention that's identical to what we had if the keys from the future just didn't exist. Another practical use case for attention masks is when we need to pad out sequences so that all sequences in a batch have the same length. We can use an attention mask to mask out all padded tokens by setting the respective key columns to negative infinity in the affinity scores. We don't need to do anything about the queries from the padded tokens, that is, the rows in the affinity scores. They'll be somewhat random, but we can just use the same attention mask in all following attention layers as well. This way, the results can't be attended and don't affect the output. The last problem of attention we'll talk about is permutation invariance. Let's walk through what happens when we change up the order of the inputs. Swapping two inputs is also swapping the queries, and with that the rows in the affinity scores. At the same time, it will swap the keys and with that the columns in the affinity scores. The swapped columns and rows are directly mirrored by the normalized attention scores, and the values swap as well. But if we think about it, changing the order of the attention columns and the values doesn't make any difference, since they are summed up after weighting the value vectors anyway. This means we can swap the value vectors and the columns back. All that changed now is that the order of the rows was changed, which does nothing but change the order of the outputs. All in all, changing the order of the input did nothing but change the order of the output in the same way. This means the order of the inputs isn't considered at all by the model, and that's a big problem. You can think about how well you could sum up the content of a page if the words just came to you in a random order. The way this problem is handled is by adding positional encodings to the very first input of the model. A positional encoding is a vector that is only dependent on the index of the token in sequence. These positional encodings can be either static encodings, like sinusoidal encodings that sample values from sine functions with different frequencies, or learned encodings that are just randomly initialized at the start and learned, giving the model the possibility to decide on its own how it wants to represent the positions. Both are about equally effective. Using sinusoidal encodings, the model can sometimes learn the structure of the encodings and understand how to interpret the encodings of positions that are beyond the sequence length the model was trained on. Learned encodings, on the other side, have more flexibility and are easier to implement. In AlphaFold and in the tutorial notebook for this video, we'll use learned encodings. To close off on attention, we want to take a quick look at the transformer architecture. The transformer was the architecture that really kicked off attention in natural language processing. What's funny about it is that it's actually really simple, particularly compared to something like AlphaFold. AlphaFold is way more complex than GPT-2 due to the more intricate format of the inputs and outputs for protein structure prediction. Shown here is the basic transformer architecture. On the left is the encoder part, and on the right is the decoder part. This is the typical architecture used for sequence-to-sequence tasks, like translation. Looking at the encoder, the only part we haven't discussed yet is the add and norm section. It means adding up the two connected inputs and performing layer normalization. Layer normalization is normalization along the channel dimension. That means subtracting the mean and dividing by the standard deviation for each entry in the sequence individually. The addition in the add and norm part is called a residual connection or skip connection. It looks innocent enough, but its introduction had huge impact on machine learning. The introduction of residual connections greatly improved gradient flow networks, and it's what made deep architectures possible. Before using residual connections, we were stuck on models of around 20 to 30 layers before training failed, limiting the capacity of the models. The first models using residual connections, ResNets, jumped up to 152 layers with a direct boost in performance. The feed-forward part in the transformer denotes a 2-layer feed-forward neural network, like we've seen in the last video. It transforms each of the vectors individually, meaning the only crosstalk between the different tokens happens with attention. Putting all of that together, the encoder consists of adding input encodings, followed by a number of attention blocks that do multi-head-attention, a residual connection with normalization, feed-forward, and a residual connection with normalization again. Don't miss out on the n times next to the encoder and decoder blocks. It means multiple copies of these blocks are stacked on top of each other, each with their own weights. The encoder is what we'll use in the tutorials, where we implement it to do sentiment analysis on movie reviews, classifying them as either positive or negative. It's also the only part that's used in modern large language models like GPT-2, with the only difference being the use of causal attention masks like we've seen before. For that use, it is trained on next word prediction. For our task of sentiment analysis, we'll simply use one of the output vectors, concretely the one at the first position, to do the prediction. We pass it through a 2-layer feed-forward neural network to get our classification. The encoder can use all its previous layers to aggregate the information of the text in the token. The full encoder-decoder architecture, like shown here, is typically used for sequence-to-sequence tasks like translation. Now, in 2024, you know that translation can be done just as well by a large model like ChatGPT using only the encoder and next word prediction. But back then, we needed to compensate for the smaller model size by more concrete connections. The decoder consists mostly of layers you already know. Here, the masked MultiHeadAttention module means attention masked with the causal stairform attention masks. More interesting is the cross-attention block that comes after the masked attention. It uses the final outputs from the encoder to create the key and value embeddings in each block, and the values that are propagated in the decoder block are just used to create the query embeddings. I think this is really interesting. All the blocks in the decoder are just used to incrementally improve the queries, that is, which of the encoder outputs each position should attend to. If you wanted to use this architecture for translation, you'd feed the original sentence into the encoder. The input for the decoder would be the translated version, shifted right by introduction of an additional start token at the beginning, and the labels would be the unshifted translated version. During inference, the decoder would be executed once for each token that's being generated, the input being the start token and all tokens that have been generated so far. This is done until the decoder outputs the stop token. With that, we are done with our introduction to attention. It's a really cool mechanism, it's not too difficult to understand and implement, and it's just everywhere in machine learning. With our intro to attention, we are done with the introductory material, and in the next video we'll start with AlphaFold specific content. Concretely, we'll implement feature extraction for AlphaFold, which in this case means going from a text file of sequence alignment data to tensors. However, you still need to finish the notebook for this video, in which we'll implement the MultiHeadAttention module that we'll use in the actual AlphaFold implementation. Aside of that, a big part of the notebook is devoted to the implementation of the transformer encoder for sequence classification. I think you can learn a lot there, on the architecture itself, but also on training models, and on transfer learning, which means taking a model that was trained on a different task and fine-tuning it to a new task. So, see you in the next video and happy coding!